What if a wood stove design could extract 90% more heat from the same amount of fuel while producing dramatically cleaner emissions and radiating gentle warmth for 24 hours after a single brief burn? That's not wishful thinking. That's the documented performance of rocket mass heaters, a contemporary refinement of traditional Finnish and Russian masonry heater principles that achieves combustion efficiency, rivaling the best modern stoves while adding thermal mass benefits that conventional stoves cannot provide. The performance seems impossible until you understand the physics. Conventional wood stoves burn fuel at relatively low temperatures, produce incomplete combustion that wastes substantial energy as unburned smoke and creosote, and radiate heat primarily while fires burn. Rocket mass heaters force combustion gases through a specially designed burn tunnel that achieves temperatures above 2,000 degrees Fahrenheit, burning fuel almost completely and extracting virtually all its thermal energy. That captured heat then transfers to a thermal mass, typically a cob bench or masonry structure, that stores heat and releases it gradually over 12 to 24 hours. The result delivers comfort that conventional wood stoves cannot match while burning a fraction of the fuel. Understanding how rocket mass heaters work, what building them requires, and where the approach fits contemporary situations helps explain why a growing community of builders and homeowners considers this technology revolutionary despite its ancient origins in Finnish, Russian, and Chinese heating traditions. The basic physics of rocket mass heaters combine two distinct principles into an integrated system. The rocket stove combustion core achieves extremely high temperatures through careful control of airflow, fuel feeding, and exhaust routing. The J-tube design that most rocket mass heaters employ feeds fuel vertically into a horizontal burn tunnel that rises into an insulated heat riser. The heat riser's intense temperature creates strong draft that pulls air and fuel gases through the burn tunnel at high velocities, mixing thoroughly and combusting completely. The complete combustion extracts nearly all available chemical energy from the fuel while producing minimal smoke, emissions, or creosote. The exhaust then enters a horizontal flue system routed through thermal mass structures that absorb the remaining heat before gases exit to the outdoors at low temperatures. The thermal mass that rocket mass heaters incorporate distinguishes them fundamentally from conventional wood stoves. The cob benches or masonry structures that surround the exhaust flue absorb heat from the flue gases and store it in their thermal mass. The stored heat then radiates into living spaces, gradually over extended periods after the fire burns out. A typical rocket mass heater might burn hot for 1 to 3 hours, then radiate gentle warmth from its thermal mass for 12 to 24 hours afterward. The extended heat release pattern produces comfort that conventional wood stoves cannot provide, eliminating the temperature swings that stoves create as fires burn hot, then die. The historical origins of rocket mass heater concepts trace through multiple heating traditions that separately developed mass heating approaches. Finnish masonry heaters called kakaluni featured heavy masonry construction that absorbed heat from wood fires and radiated it gradually into living spaces. Russian masonry heaters called pechka performed similar functions with regional design variations. Chinese Kong heated platforms integrated heating with sleeping surfaces. All these traditions recognized that extracting maximum heat from wood combustion while storing it for gradual release produces superior heating outcomes compared to stoves that radiate heat only during active burning. Contemporary rocket mass heater designs synthesize insights from these traditions with modern combustion engineering to achieve performance exceeding traditional precedents. Dr. Erkki Mustajärvi-Lahtinen, a Finnish combustion engineer who has studied traditional masonry heating systems for over 3 decades, has documented how traditional Finnish heaters achieved combustion efficiency approaching 90% through their intensive burning and mass storage principles. His analysis of both traditional and contemporary rocket mass heater designs confirms that properly constructed systems deliver heating performance that no conventional wood stove can match, with fuel requirements reduced by 70 to 90% compared to stoves heating equivalent spaces. The performance gains reflect superior application of fundamental combustion and heat transfer physics rather than exotic technology. The fuel efficiency of rocket mass heaters produces dramatic consumption reductions compared to conventional wood stoves. A typical rocket mass heater might burn 1 to 2 small armloads of wood daily to heat a well-insulated home in moderate climates, compared to 3 to 6 armloads for conventional stoves producing less comfortable heating. Annual wood consumption for typical homes drops from 4 to 8 cords for conventional stoves to 0.5 to 1.5 cords for rocket mass heaters heating equivalent spaces. The consumption reductions translate directly into reduced labor for wood gathering, reduced forest impacts, and reduced emissions across the heating season. Patricia Whitmore Henderson, a natural building instructor based in rural Oregon who has taught rocket mass heater construction to hundreds of students over 20 years, has documented how her students' completed heaters have delivered consistent performance across diverse climates and house configurations. Her teaching emphasizes that successful rocket mass heaters require attention to fundamental physics principles rather than slavish copying of specific designs, with appropriate adaptations for specific contexts, producing reliable results. The educational approach has contributed significantly to contemporary rocket mass heater adoption by providing accessible training that bridges between traditional masonry heater knowledge and contemporary DIY capacity. The construction requirements for rocket mass heaters vary substantially based on design complexity and performance targets. Simple outdoor cob bench designs can be completed by modest-skill DIY builders in several weekends at costs of $200 to $500 for materials. Sophisticated indoor systems with refined appearances and optimized performance may require $1,000 to $3,000 and skilled construction help. The cost range accommodates diverse budgets while delivering substantial heating benefits. Material requirements typically include fire brick for the combustion core, cob for thermal mass, metal stovepipe for exhaust routing, and various supporting materials. Most materials are widely available through conventional building supply channels. Now for the obstacles and limitations that affect rocket mass heater adoption. First, the building code complications in most jurisdictions affect legal installation in primary residences. Most building codes recognize only certified wood stoves meeting specific EPA emission standards, rather than custom-built heating appliances of any sort. Rocket mass heaters' non-standard construction typically falls outside code compliance pathways that conventional stoves and masonry heaters provide through certified products and licensed installer networks. The code complications have restricted rocket mass heater adoption primarily to off-grid homes, outbuildings, and jurisdictions with more flexible code enforcement. Second, the space requirements for rocket mass heaters exceed what conventional stoves occupy. The thermal mass bench typically requires 6 to 12 feet of floor space, substantially more than the compact footprint that conventional stoves occupy. The space considerations restrict applications to homes with adequate available floor area, particularly near structural walls where mass bench construction makes sense. Small homes may not accommodate rocket mass heater installations without substantial reconfiguration of living space arrangements. Third, the construction skill requirements for successful rocket mass heaters exceed what typical homeowners possess without dedicated training. The combustion core construction particularly demands careful attention to specific dimensions, material selections, and assembly details that affect whether installations function correctly. Mistakes in construction can produce heaters that smoke, fail to draft properly, or perform poorly overall. Workshop training with experienced instructors substantially improves success rates compared to self-taught attempts relying on written instructions alone. Fourth, the aesthetic considerations of rocket mass heater appearance may concern homeowners accustomed to conventional stove aesthetics. The typical cob bench construction produces organic earthen appearances quite different from the metallic industrial appearance of conventional stoves. While many natural building enthusiasts appreciate the rustic aesthetics, other homeowners find them unacceptable for their home interiors. Alternative construction approaches, using brick, stone, or tile finishes, can produce more conventional appearances at higher costs and construction complexity. Fifth, the operational considerations for rocket mass heaters differ from conventional stoves in ways requiring adjustment. The short, intense burns that rocket mass heaters use contrast with the long, slow burns that conventional stoves permit. Users must feed fuel more actively during burning phases while adapting to the different heating rhythm that rocket mass heaters produce. The operational differences require some behavior adjustment from users accustomed to conventional stove operation, though most users adapt readily within a heating season of regular use. Despite these considerations, rocket mass heaters represent remarkable heating technology that deserves serious consideration for appropriate situations where their advantages can be realized fully. The applications that particularly suit rocket mass heaters include off-grid homes requiring reliable wood heating without dependence on utility systems, homesteads with abundant wood supply where maximizing fuel efficiency reduces labor requirements, workshops and outbuildings where code compliance pressures are lower, natural building projects where aesthetic alignment supports the approach, and educational facilities where demonstration value complements practical heating benefits. These applications represent contexts where rocket mass heater advantages outweigh the complications of specialized construction and non-standard appearance. The environmental advantages of rocket mass heaters extend beyond fuel efficiency to include dramatically reduced emissions. The complete combustion that rocket mass heaters achieve produces particulate emissions 80 to 95% below conventional wood stoves even before considering fuel consumption differences. The reduced emissions address air quality concerns that constrain wood heating acceptance. In many regions, potentially enabling wood heating in contexts where conventional stove emissions would be problematic. The environmental performance rivals or exceeds pellet stoves and many gas heating approaches when measured on total life cycle impacts. Cornelius Adebayo Williams, an environmental engineer who has measured emissions from diverse wood heating appliances, including traditional stoves, certified stoves, pellet stoves, and rocket mass heaters, has published comparative data showing that well-constructed rocket mass heaters produce emissions profiles comparable to natural gas heating while using renewable fuel. His measurements demonstrate that the combustion efficiency claims for rocket mass heaters aren't exaggerated marketing, but reflect genuinely superior performance achievable through careful design and construction. The performance data provides evidence-based foundation for regulatory discussions about potential pathways for rocket mass heater code recognition. The educational community around rocket mass heaters produces accessible resources that support contemporary adoption by interested homeowners. Books by Ianto Evans and Leslie Jackson have documented designs and construction techniques. The Permies Forum hosts extensive discussions among experienced builders, sharing insights and supporting newer builders. Workshop networks across North America offer hands-on training opportunities. Online video resources show construction processes in detail. The robust educational ecosystem supports motivated builders in developing the knowledge necessary for successful construction despite the technology's non-standard nature. The economic case for rocket mass heater adoption varies substantially with wood supply situations. Households with free or low-cost wood access through their own property, agricultural sources, or local recycling channels achieve dramatic heating cost reductions that make rocket mass heater investment easily justified. Households purchasing cordwood at market prices still benefit substantially from the consumption reductions that rocket mass heaters produce. Households without wood access cannot benefit from wood-fueled heating, regardless of appliance efficiency, limiting applicability to contexts where wood supply makes sense economically and logistically. Fatima Al-Mansour Rashid, an energy poverty researcher studying heating access in rural communities, has documented how rocket mass heaters could address heating challenges in regions where conventional heating options are inaccessible or unaffordable, while wood resources remain available. Her research examines how community-scale rocket mass heater construction programs could deliver reliable heating to underserved households while building local skills and reducing dependence on imported fuels or electricity. The community applications particularly matter in regions where conventional heating infrastructure is limited and where traditional heating knowledge could be renewed and adapted through contemporary rocket mass heater approaches. The maintenance requirements for rocket mass heaters are minimal compared to conventional stoves, despite the construction complexity. The complete combustion that rocket mass heaters achieve produces minimal creosote buildup, reducing chimney cleaning frequency to annual or less frequent intervals. The thermal mass structures require no regular maintenance beyond occasional cosmetic touch-ups to cob surfaces. The combustion core components have demonstrated lifespans of 10 to 30 years before requiring replacement of firebrick elements that see the most extreme thermal conditions. The low maintenance requirements offset the higher initial construction effort across extended operational periods. The safety track record of well-constructed rocket mass heaters supports the technology's viability despite non-standard configurations. No comprehensive database tracks rocket mass heater performance, but the community of builders reports reliable operation with safety records comparable to or exceeding conventional wood stoves. The complete combustion eliminates creosote hazards that cause many chimney fires in conventional installations. The thermal mass reduces fire risks by containing heat within massive structures rather than radiating it from metal stove surfaces. Proper clearance to combustibles and routine inspection produce safe installations that operate reliably across decades of use. The integration of rocket mass heaters with domestic hot water production creates particularly attractive dual-purpose systems in some installations. Heat exchangers integrated into the combustion path can extract heat for domestic water heating, while the primary heating function continues unchanged. The combined heating and hot water production extracts even more value from the fuel while reducing the need for separate water heating systems. The integration complexity requires more sophisticated designs, but delivers substantial additional value for households interested in comprehensive energy efficiency. The technical evolution of rocket mass heater designs across the past 15 years has produced significant refinements that address early shortcomings while expanding applications. The J-tube burn tunnel configurations that dominated early designs have been supplemented by batch box designs that accept larger loads of fuel and operate with longer burn cycles more compatible with contemporary household schedules. Shippable thermal mass components eliminate the extensive site construction that traditional designs require, enabling adoption in contexts where site cob construction would be impractical. These refinements have broadened the applicable situations substantially while preserving the core efficiency advantages that define the technology. Contemporary builders have more design options than previous generations, with selection guidance available through educational resources that match specific designs to specific applications. Tobias Lindqvist Bergman, a Swedish natural building specialist who has constructed dozens of rocket mass heaters across Scandinavia over 15 years, has documented how Nordic climate considerations affect optimal rocket mass heater design. His cold climate adaptations emphasize larger thermal mass capacities to carry heat through longer cold periods, more thorough insulation of combustion cores to maintain complete combustion at extreme outdoor temperatures, and careful attention to exhaust routing to prevent moisture condensation in extended cold weather operation. The regional adaptations demonstrate how universal principles translate into specific implementations appropriate for specific climates, producing heaters optimized for their operating contexts rather than generic designs that compromise for unclear conditions. The community knowledge sharing around rocket mass heaters through online forums, workshops, and published resources represents a remarkable example of open-source technology development outside conventional commercial channels. The Permies Forum hosts thousands of detailed discussions capturing builder experiences across diverse contexts. Published books provide comprehensive construction guidance. YouTube channels document construction processes in detail. Workshop networks provide hands-on training. The community infrastructure supports motivated builders while continuously refining collective understanding through shared experience. The open knowledge sharing contrasts with the proprietary product development that dominates conventional heating equipment, demonstrating alternative pathways for technology development that may prove particularly valuable for sustainability-oriented applications. The fuel source flexibility of rocket mass heaters extends beyond conventional cordwood to include substantially diverse biomass inputs. Small diameter branches, bamboo, agricultural residues, and wood scraps all burn effectively in rocket mass heater combustion cores, expanding the practical fuel base for households with limited access to conventional cordwood. The ability to burn fuels that conventional stoves reject opens heating options. For households relying on property maintenance byproducts, agricultural operations with crop residue streams, and urban contexts where wood scraps from construction and tree service operations provide inexpensive fuel. The fuel flexibility contributes to the technology's applicability across diverse contexts while reducing pressure on mature forest resources that conventional cordwood typically demands. Yuki Watanabe Takahashi, a sustainability instructor based in rural Japan who has integrated rocket mass heater construction into permaculture education programs, has documented how Japanese adaptations of the approach integrate with traditional bamboo management and Satayama forest stewardship practices. Her programs demonstrate how rocket mass heater fuel requirements align with ecological forest management that produces abundant small-diameter material through thinning and coppice management while building sustainable harvest patterns. The integration connects heating technology with broader land management in ways that serve multiple goals simultaneously, producing systems more sustainable than either heating technology or forest management could achieve independently. The cultural significance of rocket mass heaters within natural building and permaculture communities extends beyond pure heating function to represent commitments to sustainability, self-reliance, and traditional skill revival. Builders describe the construction process as meaningful beyond merely producing heating equipment, with the hands-on cob work and masonry construction connecting them with traditional building heritage. The resulting heaters become features of homes that express values alongside providing practical function. The cultural dimensions matter to adopters in ways that pure performance specifications cannot capture, supporting continued enthusiasm and development of the technology despite regulatory complications that limit mainstream adoption. The research and development continuing around rocket mass heater optimization produces steady performance improvements through collective experimentation and documentation. Builders across continents share test data about combustion efficiency, emissions, heat transfer effectiveness, and durability. Thermal mass material comparisons, fire brick specifications, and exhaust routing refinements all benefit from ongoing refinement. The collaborative improvement process, conducted largely outside formal research institutions, demonstrates how distributed experimentation can advance technology effectively when motivated communities share findings openly. Contemporary rocket mass heaters perform substantially better than early versions from the 1990s, with continued refinement likely to produce further improvements over coming decades. Consider what rocket mass heaters mean for contemporary households interested in wood heating efficiency, off-grid heating reliability, or natural building integration. The dramatic fuel efficiency of 70 to 90% reductions, compared to conventional stoves, produces substantial environmental and practical benefits. The extended heat release from thermal mass delivers comfort superior to conventional stove heating patterns. The clean emissions address air quality concerns that constrain wood heating in many regions. The cost accessibility through DIY construction enables adoption by households lacking budgets for expensive conventional heating equipment. The educational resources support motivated builders despite the technology's non-standard nature. The integration with natural building traditions honors heritage while addressing contemporary sustainability concerns. The question isn't whether rocket mass heaters deserve consideration for appropriate situations. The question is why building codes remain largely closed to a technology that outperforms certified alternatives on most measurable criteria. The answers involve regulatory inertia and certification pathway limitations rather than legitimate concerns about performance or safety. For any household exploring wood heating options with appropriate context for rocket mass heater construction, the technology offers remarkable combination of efficiency, comfort, and sustainability that conventional alternatives cannot match.